Alright, this is video lecture number 9 for Math 5500 Regression 1. Okay. Alright, so in my previous video lecture, I was in this slide, okay, and at the end, the video ended up without proper closing, so sorry about that. So let me recall how we did at that time, okay. So X has a distribution. Does X have a normal distribution or not? We don't know, okay. So the distribution of X is unknown here. The mean is 72, population mean, and the population standard deviation is 8, okay. If the sample size is 16, the distribution of X bar we don't know. Can we say anything? No, because the population distribution is normal, we don't know, okay. What is the distribution of X bar? We don't know, because X has an unknown distribution, the sample size is small. If you go here, it says the distribution is normal. As long as the population is normal, whatever the sample size is, okay, X bar is normal. Yes. Here, how did you do this problem at that time? We discussed this in the previous video. So what we did was something like this. So this is the probability, right? 60, subtract the mean. The mean is 72, divide by the standard deviation. Standard deviation is sigma is 8, divide by n, the sample size n is 16. This becomes G, right? And then this was 76, subtract the mean, divide by the standard deviation, right? So this is -6, I don't know, 12, I don't know, -6, yes. And then this becomes, I guess, 2, right? Either way. And then what do you do? Go to the chart for this. Go to the chart for this. Okay, no, so not 0, whatever it is. So you'll get the answer in this way, okay. This is how we ended up with video lecture number 14, sorry, video lecture number 8, okay. And this one starts from page 40 to today. Suppose X has a distribution. Again, the distribution of X is unknown. The mean is 15 and the standard deviation is 14, okay. In this case, the sample size is given 49, okay. The sample size is 49. So what they're asking here, mu X bar. Since the sample size is pretty big, so the central limit theorem will work here, okay. So how do you get a mu X bar, right? So mu X bar, this guy is equal to mu is equal to 15, that's the answer, right? And then you need sigma X bar is equal to sigma divided by square root of n. Sigma is 14, square root of 49, 7 is equal to 2, right? We did this, okay. Let me do this part. This part I'll do over here, okay. I'll do here this part. So 15, the probability 15 X bar 17, the same concept as the one I did in the previous slide. 15, subtract the mean, okay. So the subtract is again 15, divide by the standard deviation. The standard deviation, remember, that should be the standard deviation of X bar. That's not this one, that is this guy, okay. 2, and then this one is 17 minus 15 divided by 2, right? So, oh sorry, sorry about that. And then this part becomes 0. And this is 17 minus 15, 2 divided by 2 is 1. And then you'll go to the chart for this, subtract, and you'll get the answer. Slide 41 and then 42 are very similar. Okay, so again here size 64, again the central limit theorem will work. So please work on this problem. Part B you work on your own. This is part A. Okay, I just did part A. Please, part B you do on your own. Okay, go to slide number 43 here. Suppose the height of 18-year-old man. Okay, this is how old the man is, so this has nothing to do. Whatever age is, that's okay. Approximately normal. This means that x is normal, right? And then the mean is 68 right here. The mean is 68. The standard deviation is 3. Okay, what is the probability that n, that means only one 18-year-old man, only one person, right, selected at random is between 67 and 69. So what they're asking here, the probability that 67 is here, 69 is here, x is here. Okay, find the probability that 67 and then 69, x is in between 67 and 69. This is what they're asking. This is not x bar, this is x only. Okay, remember, this is just x, this is not x bar. Okay, then you can convert this into g and then you can do it. How about here, a random sample of 9. So this says n is equal to 9. You need the probability that 67 is here, x bar 69, and then you'll be able to do this one now. Okay, so very similar to slide 41, 42. Okay, so let's move a little fast now. So far we did the sampling distribution for mean. Okay, so far we did, let me write down that here. So far we did the sampling distribution for S means, let me write down that. We did the sampling distribution for mean. The formula were like this: mu x bar mu sigma x bar. This is what we did, right? This is little different one. This is for the proportion. Okay, review of binomial probability. I explained binomial probability a lot, like in the second week or the first week. And you fill up this here. What is n? N is the number of trials. Okay, n is the number of trials in binomial distribution. X is, what is x? Can you think about this? Number of successes. Okay, this is the probability of success, p. This is the probability of failure, q. Remember, p plus q is equal to 1. Okay, remember, this is the total number of trials. Write down this here, the total number of trials. This is the number of successes. Okay, and then remember here, p hat is equal to x divided by n. Okay, and then this is the new thing, the proportion is p hat is equal to x divided by n. Remember this thing. Mu is the mean for the binomial probability, that is n times p, and the sigma is equal to n times q. This is what we did earlier. Okay, p hat is equal to x divided by n. I want to give you an example. In our class, of 15 people, okay, in our class of 15 people including myself, let's say 10 of us drink coffee. Okay, in our class of 15 people, 10 of us drink coffee. What is the proportion? Find the proportion of the people who drink coffee. How do you find that? Okay, so the total number of people n is equal to 50. 10 of us drink coffee, x is equal to 10. The proportion is equal to x divided by n, that is 10 divided by 15 equals 0.67, something like that. Okay, this is p hat. That's what p hat means. Okay, and remember, if you need q hat, then you can do 1 minus p hat. Remember, p hat plus q hat is equal to 1. Okay, p hat plus q hat is equal to 1, so you got p hat is equal to 0.67. If you need q hat, then it will come 0.33, something like that. Okay, all right, now we'll start sampling distribution for proportion. Okay, I explained earlier p hat is equal to x divided by n. Okay, but before you use the sampling distribution for a proportion, you need to check a condition. The condition is n times p should be greater than 10, n times q should be greater than 10. If these two conditions are good, if these two conditions hold, then p hat can be approximated by a normal random variable. Remember, n, p, p hat, these are coming from binomial distribution. Okay, there is a connection between binomial distribution and a normal distribution here. Okay, this p hat is equal to x divided by n. This is coming from a binomial distribution that can be approximated by a normal random variable x with mean mu p hat is equal to p, and the standard deviation sigma p hat is equal to pq divided by n. So let me tell you what these things mean. When you did the central limit theorem for mean, the central limit theorem for mean, we had this formula: mu x bar is equal to mu, sigma x bar is equal to, this is the central limit theorem for mean, right? Mu x bar is equal to mu, sigma x bar is equal to sigma divided by square root of n. This is the central limit theorem for mean. This slide 45, is for the central limit theorem for the proportion. Okay, central limit theorem for the proportion. Okay, so this is mu p hat. Let's say central limit theorem for mean here, and then this is for proportion, to be more specific. Okay, mu p hat is equal to p. P is the population proportion, p hat is the sample proportion. Okay, remember, p hat is the sample proportion, p is the population proportion. P hat and then p are like very similar to x bar and mu. Okay, so and then standard deviation of p hat is equal to pq divided by n. But remember, to use this condition, you need to double check this condition holds. Okay, then only. Go to the example here. Can p hat be used to approximate the normal random variable when n is equal to 8 and then p is equal to 0.7? Well, I need to check we can approximate p hat with a normal random variable or not. To check the condition is right here. Okay, n times p bigger than 10, n times q bigger than 10. Okay, n times p, n is 8 times 0.7, this is equal to 5.6, right? Is this bigger than 10? No, right? Not bigger than 10, so we can not. Okay, if this would be true, you have to try one more. You need to try n times q as well, and then that also should be bigger than 10. Okay, that is the condition. How about the second example? N is equal to 34. Suppose we have a binomial distribution with n is equal to 34 trials, and then p is equal to 0.4. Okay, in this case, can p hat be used to approximate the normal random variable? That is the question. Here we could not, because it was less than 10. How about here? N times p, that should be bigger than 10. Okay, in this example, n times p should be bigger than 10. You try, the q becomes 0.6, right? And then n times q also becomes bigger than 6, so you'll say yes. Okay, so let me show that to you here. All right, in this example, n is equal to 34, p is equal to 0.4, q is equal to how much? 0.6. How did I get this? This is 0.4, q is equal to 0.6. That sum up to 1, right? So n times p is 34 times how much is 0.4, right? 0.4. Okay, so 13 times 0.4 is equal to whatever this comes bigger than 10. You can try. And then n times q is 34 times 0.6. This also comes something bigger than 10. Then you'll answer yes, p hat can be used to approximate the normal random variable in this case. Okay, 45 we did. We'll go to 46 now. Okay, 25% of the adults often purchase used items. Okay, so 25% do that. That means p is equal to 0.25, right? And the sample of 75 adults, n is equal to 75. Okay, and p hat is the sample proportion. That's okay. This is the population proportion. P hat is the sample proportion. Okay, so if you have p is equal to 0.25, that means q is equal to 0.75. We know that, right? All right, is it appropriate to approximate p hat with a normal random variable? You need to check n times p bigger than 10, n times q bigger than 10. You need to try this. If yes, then you'll say yes, it is okay, otherwise no. Okay, check these things. What are the values of mu p hat, sigma p hat? The formula will be mu p hat is equal to p equals 0.25. We are done, right? Now you need sigma p hat, right? The formula for sigma p hat is equal to pq divided by n, right? Go here, right here, pq divided by n, the square root, right? P is 0.25 times q is 0.75 divided by n. N is 75, right? This is how it is. Okay, all right, so we did the sampling distribution for mean, and we also did the sampling distribution for the proportion. Okay, next I'll go to the estimation. In estimation we will do confidence interval. Confidence interval, okay? Okay, so estimating mu when sigma is known. You will find the confidence interval for mean in two cases. You'll find the confidence interval for this mu in two cases. One case is sigma is known, one case is sigma is unknown. Okay, remember, if sigma is known, you'll be using G critical value. Remember, if sigma is known, you will be using G critical value, and if sigma is unknown, in that case you will be using T critical value. Okay, recall, sigma is known, you will be using G critical value. Sigma is unknown, you will be using T critical values. Okay, maybe you did this in your basic stats course, but you need to make sure the assumptions meet. Okay, you have a simple random sample, or in simple words, you need to have a random sample of size n. Okay, that should be random sample of size n drawn from a population of x values. Okay, the value of sigma is, you need the value of sigma is known. If x distribution is known to be normal, let's do, if x distribution is normal, then our method works for any sample size. Remember, whenever you are finding the confidence interval, if x is normal, any sample size is okay. Sample size is equal to 2, 10, 20, 50, 99, whatever sample size is okay if x distribution is normal. If x has an unknown distribution, if x is not normal, we require a sample size of 30 or greater. Okay, you need the sample size of 30 or greater. That means n should be greater than or equal to 30 if x has unknown distribution. In other words, the conditions of central limit theorem should meet here. Okay, remember, either the sample size should be bigger than 30 or the population should be normal. One of these conditions should meet. Recall again, when I did in the beginning, maybe first or the second video lecture, I called this as statistic, and I call this as the parameter. Anything you calculate from the population, this is for mean, right? This is for the standard deviation, this is for variance, and this is for proportion. Okay, this is for mean, this is for the standard deviation, this is for the variance, and this is for proportion. All these, this column is for the population, this is for population. Same thing for sample, same thing for the sample, that is called statistic. And in this confidence interval chapter, sometimes they call it point estimate. Point estimate is nothing more than the statistic, exactly the same thing. Statistic and the point estimate, same thing. Okay, the mean is mu if it is for the population, mean is x bar if it is for sample. If the standard deviation is for the population, that is sigma. The standard deviation for the sample, s. The variance for the sample, s squared. Proportion for the sample, p hat. Okay, and remember, p hat is equal to x divided by n. We just did in previous like 1 or 2 slides before, right? All right. Confidence interval. What is a confidence interval? Often we seek a range of values or an interval for the unknown parameter. Okay, that range of values is called confidence interval. We want to have some confidence that the interval covers the parameter. That interval is called the confidence interval. The notation is CI. And we use the central limit theorem or normal approximation to binomial. What this means, I'll show you in the coming slides. Okay. All right. Once again, finding the confidence interval for mean, mu. One thing you remember, we find the confidence interval for the parameter. Note this thing. We find confidence interval for parameter. And then that parameter is the mean here. Okay. Always we find the confidence interval for the parameter, not for a statistic. Remember, we find confidence interval for the parameter, not for a statistic. We find the confidence interval for the parameter, not for a statistic. We use statistic to find the confidence interval for the parameter. That's what it is. So I have a random sample from a normal distribution. Oh yes, the distribution is normal here. Okay, they have given that, and the sigma is known. Okay, in that condition, again once the condition, the population is normal and the sigma is known. In that case, x bar minus g critical times sigma divided by square root of n, and then minus the same thing is here plus. Okay, this is called the confidence interval. Okay, where g critical is called, gc is called a critical value. The critical values are given below. 70% confidence interval, this is g critical. 70% confidence interval you need, the g critical is 1.04. 75% is confidence interval you need, the g critical is 1.15. 80% confidence interval you need, the g critical is 1.28, all the way until very popular, used very often. This is the one you need 95% confidence interval, and then you will be using g critical 1.96. Hold on a second, I want to show you where this chart came from. I'm telling you now, if you need 95% confidence interval, g critical is 1.96. I'll show you where this is coming from. Okay, give me a second. Okay, I told you 95% confidence interval, the g critical is 1.96. That is what I told you, right here. See, if you need 95% confidence interval, the g critical is 1.96. If you need 90% confidence interval, the g critical is 1.645. Okay, this chart is given to you. I sent in email, I guess, or yeah, anyway, I have given this chart to you. If you don't have this chart, please let me know. You need to use this chart when you do your homework assignment, or on test also you need to use this chart. And remember, on test you are allowed to bring this chart, the chart I provided to you. If you don't have the chart, please let me know. I'll be happy to provide you. Okay, all right, that is where this chart is coming from. Remember, this g critical is used only if sigma is known. This formula works only if sigma is known. Let me give you a formula for the confidence interval. Confidence interval for mu, that becomes x bar. We need the confidence interval for the parameter mu. We need to use the statistic x bar plus minus g critical, plus minus because minus is here and the plus is here. Okay, plus minus g critical times sigma divided by square root of n. You know what, this is x bar is the mean, and this sigma divided by square root of n is the standard deviation from the central limit theorem. Okay, mean of x bar is equal to mu, the central limit theorem. Central limit theorem was saying mean of x bar is equal to mu. sigma of x bar is equal to sigma by square root of n. This is the mean of x bar, okay, this thing, and this is x bar, okay. So this is the formula for the confidence interval for mu when sigma is known, okay. All right, I have one example for you here. A random sample is drawn from a normal population. Even previous slide we discussed the population is normal, okay, and here also we are telling the population is normal. That's good. You need to have normal population, or you need to have a bigger sample size, bigger than 30. We have a normal population, good, okay, that is the requirement. Sigma is equal to (0.33). This is what you need, okay, and the sample mean is x bar. X bar is equal to 3.15. We need the 80% confidence interval, okay. We need the 80% confidence interval. So see here, 80% confidence interval, G critical is 1.28, okay. So you have sigma, you have x bar, you have G critical, and how about n? The sample size n is random sample of size 15, right? The formula is x bar plus or minus G critical. This is all you need, right? See, once minus and once plus, and put the numbers, you'll get this thing. Interpretation. This interpretation is very important, okay. I am whatever percentage confident that the interval you just got, this interval is the one that contains the true population mean mu, okay. So this is the interpretation, and whatever the part you are adding or subtracting here, see, this part you are adding or subtracting, this is called the error, or sometimes people call it marginal error, okay. So margin of error or marginal error, the same thing. Whatever part you are adding or subtracting, G critical times sigma divided by square root of n, this piece is called the marginal error, okay. So keep this in mind. The interpretation, I'm 80% confident that the interval covers is the one that contains the true population mean mu. If you want to make this a little simple, I can give you this kind of interpretation. I am 80% confident that the true mean mu lies between how much? 3.04 and 3.26. That is maybe more easier interpretation. Same thing. I am 80% confident that the true mean, some people call it population mean, some people call it true mean, mu lies between this number and this number, okay. This is the way you do the interpretation. What if the population is not normal? What if the population is not normal? Let me tell you one thing here. This should be okay. Let me tell you one thing a little bit to emphasize here for this slide, okay. So let me create one more slide here, okay. So let me write something here to make it more clear. I told you confidence interval for mu, the formula x bar plus minus G critical sigma divided by square root of n. This is what I told, right? Now remember, this part is called marginal error. Marginal error is equal to G critical sigma divided by square root of n. Okay, let's solve this equation for n. If you solve this equation for n, then multiply by the square root of n. Marginal error is equal to G critical times sigma, right? And then if you solve this equation, that gives you n is equal to G critical sigma and then marginal error squared. This is the formula used for finding the sample size. Okay, this is the formula used for finding the sample size. Okay, in your homework problem, in homework number 2, there is one problem where you need to find the sample size, I guess. Okay, and finding the sample size, you need to use this formula, G critical sigma divided by E squared. Let me tell you what that is. Okay, homework 2, right? Okay, question number 5, number D. Find the sample size for 80% confidence interval. So this gives you G critical is equal to 1.28 or 1.04, 1.28, I guess, something like that. You'll get this thing. The error, marginal error is given here. Okay, so you need n. So how do you do this problem? N is equal to G critical sigma divided by E squared. G critical you'll get from here 1.28, I guess. Sigma is given here, and the E is the marginal error. Marginal error is here, and then whatever n comes, always round up. Always round up. For example, if it comes, just example, if it comes 15.01, so tiny, still go up, make it 16. Whatever is the sample size in terms of decimal, always round up. Even if it is 15.01, not more than like 5 here, so tiny, after 15.01, still go up, make it 16. Okay, this is the concept you need for the homework number 2, assignment number 2. Okay, all right, we'll go ahead now. So sample size n is equal to G critical sigma divided by the marginal error squared. Okay, this is used for that problem. I'll call this. I don't think you need this now, right? Okay, let's go here. Earlier we discussed if the population is normal, like here, see, I told here the population is normal. What if the population is not normal? If the population is not normal and the sample size is large, that's okay. Using the central limit theorem, G is equal to this has an approximately standard normal distribution. Okay, if the population is not normal but the sample size is big enough, bigger than 30, then we can go ahead. This is one of many practical applications for the central limit theorem. Okay, all right, confidence interval sigma known. Okay, sigma is known and the confidence interval. You read this story, okay, and this does not say anything that x is normal. Okay, x is normal, it does not say anything. Please, you go ahead and then read this problem. It does not say anything that the jogging time x is normal. It doesn't say. However, the sample size is 30. Let me write down here that for you. Here, the time, the jogging time x is not normal. but n is equal to how much? 90. N is greater than 30, right? So x bar is approximately normal. Okay, here x is not normal. The problem does not say x is normal. It does not. But remember, the sample size is 90. That is way bigger than 30. That means we can consider that x bar is not exactly. X bar is approximately normal. This is x bar. This is, it looks tiny. This is x bar. This is x bar as well. Okay, this is x bar. Okay, remember this is x bar. So how do you find the confidence interval? Same way as earlier. Only the thing new was earlier x was normal. Here x is not normal, but the sample size is bigger. Same formula. See, same formula. And then I'm 90% confident that this interval contains the true population mean. The true population mean what? Mean running time in terms of the problem. Always do the interpretation of the confidence interval in terms of the problem. So here I'm 90% confident that this interval contains the true mean running time. Okay, mu, what is the mu? Mu means the true mean running time. Okay, for her, she has, you know, the population running time, but we have the excess of sample running time only. Okay, so we have the inference for the population running mean running time. Okay, all right. We got the confidence interval, right? Here we got 90% confidence interval. Okay, now this is 53, slide 53. In slide 54, what we do is now we compute a 99% confidence interval. Everything is the same as continued. This is continued from previous slide. So here we had 90% confidence interval, and then here is 99% confidence interval. 99% means G critical is 2.58, right? See, 99% G critical is 2.58. Everything is the same, and then you do the interpretation. Find the confidence interval, and then you do the interpretation. Remember, we went from 90% to 99%. So we went to the higher confidence. Okay, we got the higher confidence, so the confidence interval became wider or shorter. Okay, you figure that out. Okay, earlier, how much was earlier? 53. We have 22 and then 22, right? 22, 22 something, right? How much here? 21, 23. This is wider. This is smaller than the earlier. This is bigger than the earlier. So earlier we had this big confidence interval. Now we have this big. Okay, this is for 90%. We have 99% here. So 99% confidence interval is longer, right, than 90% confidence interval. So what we did, we got the confidence, we gained the confidence, right, 99% from 90%, but we lost accuracy. Okay, this n is equal to G critical sigma divided by E squared. I discussed this in a couple slides ago. I wrote this formula that you need for the homework problem number 5 in assignment number 2, right? And see, the sample size depends on, the sample size depends on the G critical confidence level, right? Sigma, right? and then the marginal error. So sample size depends on these three things: G critical, sigma, and the error. That is explained here. Okay. All right. So we got the confidence interval for mu, all the three cases, right? Let's do one more. Choice of sample size for a given margin of error. So you read this example. This is straightforward. Okay. Let me go here. Computing the sample size, you try this. Okay. So assume that we want to estimate the mean IQ score for the population of stats professors. Okay. How many professors must be selected? That means they're asking you n is equal to what? If we want 95%, 95% means G critical is equal to 1.96 and sigma is given is equal to 15, right? All right, so is the question clear? How many stats professors must be selected? All right. So what is the formula? N is equal to G critical sigma divided by E squared. This is the formula, right? This is the sort of formula from slide 55, right? All right. So the G critical is 1.96, sigma is 15, and the error is, see, the sample mean is within 2 IQ points of the population mean. That means if the population mean is here, then the sample mean could be this side at a distance of 2, or this side at a distance of 2. That means the error is this guy 2 or this guy 2. Okay, that error is equal to 2. Okay, squared. So let me check how much is that. 1.96 1.96 times 15 divided by 2 squared. I got 216.09. If you use your rounding rule, then so tiny, so you'll do just 216 only, right? No, go up, make it 217. The number of people, the sample size, always round up. Okay, this is how it is. So we did the confidence interval for mean when sigma is known, when sigma is unknown, and we also did find the sample size. Okay, so this is what we did. Let's go to slide number 58 now. Computing the confidence interval and margin of error. Okay, this 40 students are selected, so the sample size n is equal to 40, right? Sorry, n is equal to 40. Sample mean x bar is 58.3, sigma is 9.5, and then G critical is equal to, see, 95%, G critical is 1.96, right? So construct a 95% confidence interval. The formula is x bar plus minus G critical sigma divided by n. Remember, in this case, the conditions meet or not. It does not say anything that the population is normal or not. Let me see. It doesn't say that population is normal, but the sample size n is equal to 40. The sample size 40 is bigger than 30, so the requirements meet, right? And then you'll plug in the numbers, you'll get the confidence interval, and then you do the interpretation. What is the margin of error? Margin of error is the guy right here. So marginal error is equal to G critical sigma divided by square root of n. G critical is 1.96 times sigma. Sigma is 9.5 divided by square root of n is 40, right? That gives you the marginal error. Okay. This is computing the confidence interval and margin of error. You try this. You try it done. You try now. Okay. Finish this. Go to 59. Continue from the last slide. How many students should be sampled? That means in this case they are asking you n, and then n means the same formula, G critical sigma divided by E squared, and then you need to round up. Okay, so G critical is the same as the one you had earlier, 95%, right? Sigma, the same thing. The marginal error is 1 second. Let me see. This is, give me 1 second. Okay, this. How much was sigma here? 9.5. So make some change here. This is not 1 second. This should be, in my belief, this should be 11 seconds. Okay, and then check the answer. Okay, so this should be marginal error. No, double check. Let me double check. This is not the standard deviation. This is the marginal error. Change it. Marginal error is equal to 1 second. Sorry about that. So the change it. Marginal error is equal to 1 second, and then do the calculations. And if the answer does not work, please let me know. What if we lower the confidence level to 80%? Do the same thing. N is equal to formula, the same formula you apply. N is equal to the same formula, but this case 80%. So G critical is 1.28. Here you have to use G critical is equal to what percentage it was? 95%. So 95% it was 1.96 here, but here same formula, same thing, use this G critical. What did you notice? That means when we had 95% confidence interval, what is the sample size? When 80% confidence interval, what is the sample size? And then what did you notice? When the confidence level goes down, the sample size goes up or goes down. You need to figure out. When the confidence level goes up or down, the sample size goes up or goes down. Figure out. Okay, from this one and then this one, you check when the confidence level goes down, like here from 90 we went to 80, and the sample size went up or the sample size went down. You figure that out. Okay, this is all for this video lecture number 9, and next video lecture will be lecture 10, and the lecture 10 will proceed from this page number 60. Okay, 59 is here, so from slide 60 we'll go ahead. Okay, all right, thank you very much. So we'll do from page number 60, slide number 60 next time. Okay, all right.